This is problem 46. It used to be a homework problem, but people got too creative with their solutions, and so now it's not a homework problem, it's an example problem, and I'll show you how creative people became with their solutions to this problem. So the intention for problem 46 was to use the formula that we have for the change in potential, and that's equal to the negative integral of E dotted with dl. And for this, I'm looking for the electric potential at the center of the sphere. The sphere has an outer radius B and inner radius A, but in this case it's a metal sphere, which means the electric field in the hollow part here is equal to 0, and in the shell is also equal to 0 because it's a metal sphere, and the total charge is Q. All of that charge is on the outside surface of the sphere. So what we would do in this place, what I thought we were supposed to do in this case, is to find the potential when r is equal to 0. We have the change in potential is the potential when r is equal to 0, which is our final point, minus the potential at our reference point when r is equal to infinity, which would be 0. So our initial point is infinity, our final point is 0, but I can't go there all at once because the electric field is different in different regions, sort of. So outside the sphere we have one electric field, so I'm going to call that electric field 1, so I can come in from infinity, go to point B, and then I have to stop at point B, and then you could go from point B to point A, and then go from A to the origin, or you could recognize that the electric field is 0 in this region here. It's also 0 in the shaded region, so we really don't have two different electric fields after we get to this point here, because it's 0 in the metal part, but it's also 0 in the hollow part. So we could actually go from 0 all the way to the origin, but let's pretend we didn't know that, or if it was plastic instead, you'd go from B to A in, let's call this region 2, so electric field 2 dotted with dl, and then you'd go from A to 0 with electric field 3, but electric field 2 and electric field 3 are both equal to 0. Okay, so that leaves me with my integral here as I go from E to B, and it's a metal sphere with a net charge of Q. So the electric field is kq over r squared in the r hat direction, dot that with dl, and you get kq over r squared dr. And then from these two terms here, I just get 0 because electric field 2 is equal to 0 and electric field 3 is also equal to 0. Okay, when I do the integral, I have r squared in the denominator, or I could say r to the negative 2 in the numerator. I raise the power. The new power is negative 1. I divide by the new power, which is negative 1, which makes that positive. So that's plus kq over r as I go from infinity to b, and then it's just plus 0, so that doesn't really matter. Okay, so this is kq over b, and then when I plug in the lower limit of integration, that's kq divided by infinity, which goes to 0. So that's our answer. And that's getting it with this formula here. Now, that's how I would solve the problem, but the creative solutions that I saw for this problem, when it used to be a homework problem, was that some people said this was k dq over r, and then the r would be a b, which we'll talk about in a moment, and then you add up all the net charge and you just get the total charge q, so that gives you kq over b. Which is correct. However, you really have to think a little bit harder about what's going on if you want to solve the problem this way. So all of the charge is on the surface of the sphere. Remember, it's a three-dimensional sphere. But if the charge is on the surface, then all of the charge you have is a distance b away from our point of interest, which is at the origin. So that distance is b. And because of that, this is like the problem we looked at earlier, where we had the thin ring and we were looking for the electric field. Let me see if I can find that. Okay, so then it becomes almost just like problem 42, except that 42 was a ring and this is a sphere, but it doesn't really matter because the charge is still the same distance, all the charge is the same distance away from the origin. Okay, so it works, but you have to think about what's actually going on if you want to use the equation this way. The other thing that I would point out is that I think this solution is actually more useful because let's suppose our point of interest wasn't at the origin, which would be the center of the sphere. Let's suppose it was anywhere else inside the sphere, so like at this point here or at that point there, then this equation here would still work. You would just go instead of, well, that would change your limit either here or here. But since these were both 0, that wouldn't really matter and you would still get the same thing. Okay, so that's problem 46, and then you have a homework problem. Hang on just a minute. Okay, so 44 was a homework problem. And 44, if you think about it, is actually similar to 46 because the fact that the sphere is hollow, if it's a metal sphere, doesn't really matter because all the charge is still on the outside surface, which may lead you to wonder how you're supposed to solve problem 44. Well, I guess my preference would be this way, but you can really solve it however you want, and as long as you get the correct answer in an appropriate way. I don't really care what method you use, but do make sure you draw the graph. And that concludes this video.